So if you go back to two-dimensional triangulations, then there's work of Steinitz from 1922 that says that every triangulation of the two-sphere can be realized by a two-dimensional, as the boundary of a two-dimensional polytope. Okay, so what does that mean? That means that, so here's an easy triangulation of a tetrahedron. But if you take any triangulation of the two-sphere, then you can think of its vertices as lying on a sphere, and you can connect lines and create this two-dimensional polytope. So you can actually, there's a geometric variation of this, which is the Kobe-Andreev-Thurston theorem. Which says that really any triangulation of the two-sphere can actually be realized as the nerve of a circle packing. And what this means in terms of hyperbolic geometry, well, okay, so let me say this. So a triangulation of the sphere, so is you have a bunch of triangles on your two-sphere, and the nerve of a circle packing just means for every one of these vertices, you can draw, you can shrink and adjust the triangulation so that the vertices of your triangulation correspond to centers of actual circles, and the edges correspond to points of tangency, and then you have these disjoint disks with these interstitial regions that are circles. So if you take this into hyperbolic geometry, so I won't go into too many details about hyperbolic space, but if you think of hyperbolic space in the upper half space model, upper half space model, then your boundary at infinity of the three-sphere you can view as the Riemann sphere, as the two-sphere, and you can put this triangulation on the this plane, and now all of the circles correspond to totally geodesic hyperplanes, and you can cut out disjoint these disjoint surfaces bounded by the hyperplanes, and you end up with, so maybe let me write some of this. So circles are geodesic hyperplanes. They correspond to geodesic hyperplanes. And if you cut them out, then this circle packing corresponds to this ideal hyperbolic polyhedron. Okay, so every triangulation of the two-sphere, in other words, is very nice. Combinatorially, it's realized as the boundary of a two-dimensional polytope. Geometrically, it can be obtained as you can make this polytope hyperbolic, and you can put all the vertices at infinity. That's what it means to be ideal. And so basically, this is all pretty well known. So 2D triangulations are nice. It's the summary of this. All right, so let's jump into 3D. So combinatorially, it's been known for a very long time, so a work of Moise from 1953, that every three-manifold decomposes into tetrahedra. And this is what we're going to call a triangulation. So in other words, we just require tetrahedra. Vertices are glued to vertices, edges to edges, faces to faces. And sometimes we have our vertices. Well, maybe let me kind of draw a picture of that. So we have these tetrahedra, and we're going to glue edges or vertices, edges, faces. Sometimes our vertices will be ideal, meaning they are removed, or you can think of them alternatively at the boundary of infinity, or sometimes they will be material. So we'll look at both types of triangulations for this talk. And triangulations of three manifolds are becoming quite important. So there are lots of applications, I guess, modern applications that maybe weren't expected in 1953. But one of these is computational topology. A lot of computational tools in three-manifold topology use triangulations to represent three manifolds. I guess there are a lot of quantum invariants as well. I'm going to write down that that take in something like a triangulation, and they'll give you a three-manifold invariant. But both of these can be difficult. You really would prefer simple triangulations. Nice triangulations. Okay, so an example of a nice triangulation. Let me say. So there are different ways to define nice. There are some combinatorial definitions of nice. There are geometric definitions of nice. Maybe since I was just talking about hyperbolic ideal polyhedra, let me just jump in and give a kind of a geometric definition. So we know, due to work of Thurston-Perelman geometrization theorem, that every three manifold decomposes into one of 8 3D geometries. So decomposition of three manifold into geometries. So it would be nice if you have a manifold for which you know a triangulation, if you could ensure that the tetrahedra, so the question, can tetrahedra be made geometric? So for example, in the hyperbolic case, there's an open conjecture that any cusped hyperbolic three manifold admits a decomposition into convex, so e.g. convex hyperbolic tetrahedra. Combinatorially, new page. An analog of Steinitz's theorem, this combinatorial theorem for the two-sphere in 2 dimensions, would be to ask if it is polytopal. So polytopal would mean, can you take a triangulation that is the boundary of a 4D polytope? And this is well known, this has been known for a long time, not to be possible. So if this is the question, here's the answer is no. Since it is known for this three-sphere, since earlier than the 1950s. Let's put 1950s-ish. So there exist triangulations of the three spheres that are not polytopal, and there are many constructions. There are different degrees of how bad do these triangulations get in terms of the combinatorics. And most of these constructions are linked to our topic of the conference here. So constructions use knot theory. And an example of this is work of Lutz from 2004, who proved that there exists a triangulation of the three-sphere with three edges forming the trefoil. And this, in particular, this will mean that you cannot have this triangulation is not polytopic, but also it has other consequences. Kind of related work is due to recent work of Burton and Key from 2023, which showed that in fact, there exist triangulations of the three-sphere where every edge is knotted. Okay, so there are some pretty awful triangulations. So today I am going to talk about a couple of questions. So number one is, how bad can a triangulation be? And the question two is, but how good? And we have a couple of results that I'm going to be discussing that kind of surprisingly to me are both quite bad and quite good, depending on how you look at them. So I'll try and explain some of that today when I tell you a little bit about this. So okay, so let me put down the main theorem. So again, this is with Diani Ibarra, Dan Matthews, myself, and Jonathan Spreer. And we showed that if you give us any knot inside of the three-sphere, then there exists, we can find a triangulation of the three-sphere with a single vertex. I should say this is a single, a single material vertex. And a distinguished edge forming the knot. And I should say too, this is all quite constructive. But what it means is there's no hope of straight edges, convex spherical triangulations. So this is, so for any knot, you can find this. But we also have, so interestingly enough, so the follow-up theorem, so same people, plus some previous work that I did with Sophie Ham, is that, in fact, if you take this distinguished edge, so we're going to take this triangulation that we have from above, so this triangulation, and you remove the distinguished edge, so including its its endpoints are this material vertex, then what you end up with is a triangulation of the complement of the knot that, in an appropriate sense, let me just say it is generically geometric. So in other words, S3 minus K will be hyperbolic. And all of the tetrahedra will be convex ideal tetrahedra. Okay, so from a geometric point of view, that's about as nice as it gets. From a combinatorial point of view, though, we can take any of our edges to be about as terrible as you would like. Okay. So I'm going to take the rest of the talk. I'll explain more about the proof, the construction of these triangulations, how we did it, and how you end up with well, how do we get our knotted edge, and then when you remove it, how do you get this geometric triangulation? And the construction uses tools from hyperbolic geometry, but the result itself in at least this first part. Maybe I should number them: theorem 1, theorem 2. Theorem 1 is purely combinatorial, and there's no geometry that's involved. Okay, so part 2. Let me say a little bit about how we got interested in this particular problem. We were actually looking at some quantum applications. And so there's this, there is a notion of what is called an H triangulation that we learned about relatively recently. And what this is it's just so an H triangulation is a one vertex triangulation of a 3-manifold with a distinguished edge forming a distinguished knot. Okay, so forming a fixed knot. And there are quantum applications. You label these appropriately, and they give you information, for example, on the volume conjecture. And these are due to people like Anderson Kashayev, Wu, Vartanov, and they found H triangulations for a few simple knots. So the figure 8 knot, figure 8, the 5-2 knot, and the 6-1 knot. So you will notice a theme. So this is all a little bit older work, but very recently, Ben Aribi, Francois Gueritode, and Higuet Nakazawa, they were able to extend this, and they found H triangulations of S3 with any twist knot. And again, and this had some consequences, so quantum consequences that I won't go into. But it's a nice paper. And the idea is what they really needed to do to get the quantum invariance out of that was to start with a really nice special ideal triangulation of the knot complement. So maybe let me kind of write down some of these ideas. So start with a geometric triangulation of the twist knot complement. And they then took this complement and they inserted one tetrahedron carefully with a distinguished edge. So insert tetrahedron. And the way that the inserted tetrahedron is, well, maybe let me just say a little bit more. So they needed a face. So you're going to cut open a face F of this triangulation that they started with. I don't know how to, maybe I should write that T of S3 minus K. So, oh, sorry. And then they have a new tetrahedron that they're going to glue on. They take this with the distinguished edge E. You're going to glue the back faces to this opened up face F, and then you fold over the front faces. So it just folds, and this edge E here in the front will become the knot. If they started out with this with a special with a triangulation that is nice enough. So maybe let me say what do you need for this to be nice enough? So really following their ideas, but generalizing this a little bit, what we found, so let me say generalizing. This is the Benaribi, Gary Toad, and the Nakazawa construction. You need a triangulation so that this face F spans a slope. So this is an ideal triangulation. A face F spans a meridian. And what do I mean by that? So if you look at the cusp view, so you have this triangulation of your knot. It's got a topologically a tubular neighborhood of the knot sitting inside of your complement is going to be a torus. And you're taking an ideal triangulation, which means that if you truncate all of the tetrahedra, so truncated tetrahedra, give a triangulation of this cusp torus. And what you require, so you'll have a bunch of tips of tetrahedra poking in here, and but you require that one of the faces of these triangles runs across an entire meridian. And this is your face F. And I have carefully taken F to form a meridian of this, but you should be thinking of the torus, right? We're going to glue here to here, we're going to glue here to here. So this is my my triangulation, and this is a face that is spanning a meridian. So once you have this, you cut along F, and you insert this special tetrahedron that's right there. Above. And the result turns out that it is a Dane filling of S3 minus K. It's called mu. So this is just going to be S3 in this case. You could do this a little bit more generally if you have any three manifold M. And the neighborhood of E is the solid torus. Let me scoot this down just a bit. Okay. So the neighborhood of E forms this Dane filling. Solid torus. And so what that means is that your result is a triangulation of the three sphere with E is now the knotted forming K. All right, so this is how we're gonna do this. We're gonna find triangulations of knot complements, ideal triangulations, for which you have a face that spans a meridian. And then all we have to do is we can cut along this face F, and we can insert this special tetrahedron. And then we know from this theorem that I'm going to get my triangulation of the three sphere with the knotted edge that I'm looking for. Okay. All right, so let me write that goal. Okay, so when we first realized that, I should say that the Benaribi and Gary Toad um, uh, Piguet Nakazawa, when we were looking through their paper, they have basically a construction that works for all of the twist knot. They build this explicitly, but we realized that we were looking at another family of knots with a very similar construction, and this is where we saw the connection between theirs and ours is just this face spanning the meridian, basically. But once you see this observation or this theorem, this observation that this construction, then you can find a lot of examples. So of knots that have this. So for example, this holds for your well-known Sakuma Weeks triangulations of all two bridge knots. Okay, so back in the 90s, Sakuma and Weeks found geometric triangulations of any two bridge knot, any hyperbolic two bridge knot. And every one of them, for those who are experts in this face that spans the meridian is where you have a hairpin turn in the triangulation of the two bridge knot. So there was something, but we can do better. So we're going to find triangulation of any knot complement that has a face that's spanning a meridian. And the way that we're going to use this, or the way that we're going to do this, is in fact it comes out of some work again that I did with Sophie Ham in 2022. We're going to use fully augmented links. So let me write fully augmented links. And I'll say a little bit more about what those are in a moment. But in my paper with Sophie, we showed that any hyperbolic fully augmented link emits a triangulation with a face spanning meridian. And in fact, when these are hyperbolic, you can take this to be a geometric triangulation. That's the result, actually, that we were interested in that paper. So let me tell you what a fully augmented link is. Actually, let me do it by way of another proposition, which is more, I would say, I guess it's kind of classical. Maybe going back to work of Thurston or so, but so every knot in the three sphere, or for every knot, S3 minus K is obtained by Dane filling a fully augmented link. And in fact, you can, okay, let me give you the proof of this. This is a proof slash definition of the fully augmented link. So start with a diagram of a knot. Okay, so here's a nice diagram of a pretzel knot. You could take any knot that you want, and you find the go finding the twist regions. So a twist region is a portion of the diagram where two strands twist around each other maximally. And so in this picture that I've got here, there are three twist regions. So here we've got two strands that are forming 1, 2, 3, 4 crossings. Here they're forming 3 crossings. This is another twist region. This is just a single crossing, but there are no, it can't be joined to any other crossings in a twist. So, okay, so you've found all of your twist regions. And then what you do is you augment. And what that means is you insert unknots. So for every twist region, you insert a little unknot, just encircling those two, or the two strands. So I guess if this is S3 minus K, then what we've really done is we've drilled out more stuff. So I'm going to call this a crossing circle. And this is a new link. But conveniently, this is homeomorphic to the thing that you get by you remove pairs of crossing. So you can do this by just cutting along. You've got this new disk now. So you spin it a full twist around, and this can remove 2 crossings at a time. And you either, you do this as much as you possibly can, and you either end up with no more crossings in your twist region, or you might have 1 left over. Okay, so this or this. So you get a totally new diagram. So this diagram here, I would put in crossing circles here, here, and here. And then when I do this homeomorphism, I have, if I've counted correctly, I have 4 crossings here, I have 3 here, and I have 1 here. And so my my link is homeomorphic to something that looks like this. Oh. Okay, so this is the construction of when I've done this for every twist region, what is left over is called a fully augmented link. But now, okay, so how is this related to the original? Well, you go back by Dane filling. And in particular, if you removed, let's see, say n pairs of crossings, then you're going to do a 1/2n Dane filling. Will give you back the original. Okay, so every knot has a diagram. Every diagram, you can identify the twist regions, and then you can insert these crossing circles, and you get that the knot was obtained by Dane filling a fully augmented link. We need to upgrade this a little bit because we only know triangulations of hyperbolic fully augmented links. And so upgrade, you can ensure that the fully augmented link is hyperbolic. Okay, and typically it will be. There are a few times when it isn't. So you have to think about what do you do with if it's a 2Q torus knot. So there's only 1 twist region. If you were to fully augment this in the obvious way, that is not going to be hyperbolic. You'll get, your 1 annulus with a crossing circle like so. So this is relatively easy. If you want to get something hyperbolic, you're just going to be super inefficient. We're going to augment the wrong way. So every one of these crossings, we made that a little bit bigger, gets its own crossing circle. And then when you do that, you will end up with something that is that's hyperbolic. And then the other thing you have to worry about to ensure that it's hyperbolic is if you have a link that's not prime. So let's see if let me draw an example. So if you have a link that's a knot, or that's not prime, I should say, we're looking at knots here. Then you would have something like this. If you were to do if you were to augment this diagram just as it is, again, you're going to get something that's not prime, and that's going to be not hyperbolic. So the fix is right, so you can augment here, 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 here. Those are all the twist regions. But then you kind of introduce a little artificial twist region as well that's going to break the this essential meridional annulus that you get when the link is not prime. Okay, and so this is kind of a quick proof that you can ensure that the fully augmented link, so a fully augmented link, or the Dane filling of a fully augmented link is hyperbolic. If you do something like this here and here, both of these instances, you would do trivial Dane filling to get things back. But that's okay. We just need that some Dane filling on a hyperbolic link will give us our original knot. Okay, so now let's find a face spanning a meridian. So there is a classical decomposition of a fully augmented link into ideal polyhedra. So, sorry, hyperbolic. And this has been used extensively in hyperbolic geometry and hyperbolic knot theory. So I'm not going to go through all the details super carefully, but basically you have these little crossing circle regions in your diagram. And the way that you decompose this is the standard picture, you put edges here in your complement of your link, and then slice up. So you've got this little two punctured disc, slice it open and flatten it down. So there are going to be two halves of this. The slice, so slice across the projection plane, slice everything open, flatten it down, and this gives you a triangulation. So notice that this particular, when you shrink these thicker lines, these are ideal vertices. They're part of the link, so they're not part of the knot, so they should be ideal. When you shrink them down, all that's left over are these red triangles. So you have these red triangles, sorry, I guess I should say red triangles, and then you've also got faces corresponding to the faces of the link. These are your faces of your polyhedron. Okay, so you can adjust this. Oh, sorry. So then I guess I should say you can subdivide this into a triangulation. Before you do that, let's adjust it a little bit. So instead of triangulating as shown above, just flip one of the edges to look like this. Okay, so this is now, I have given a, this is a new triangulation. Before this was a triangulated two puncture disc. And this, again, I just did an edge flip, basically. I have a new triangulation of a two puncture disc, but what else? This triangle that I've just shaded is now my face F. And you can see from this picture that in fact, here's a meridian right there of the knot. And so this is going to span a meridian. Okay, so then you Dane fill. Just looking at the clock, I have a few seconds left. How do you Dane fill? So you triangulate, or complete the triangulation, I should say. Or in other words, you subdivide into a triangulation. You have a space spanning a meridian. You do the Dane filling. You just do this by plugging in triangulations of solid tori. And there's a well-known way of doing this due to Jaco and Rubinstein. they have these layered solid tori, and it turns out that those work. They're just fine. You have to be a little bit careful when you're doing trivial layered solid tori, but it's not really that big of a deal. And this gives back, this gives you a triangulation of your original with this face spanning a meridian. And then you do this, this trick. You put in this special tetrahedron, and that gives the result. Okay, so I'm almost done. Let me just note one quick theorem, though. So in fact, these triangulations of these fully augmented links are, so generically, these fully augmented link triangulations are geometric. So they're quite nice. So we use these very nice geometric triangulations to construct these quite interesting combinatorial triangulations. All right, so I'll stop there. Thank you.